All right, this is our week 3, day 2 video. So we're going to be looking at a couple things. We're going to be looking at 3B1, which is over linear versus exponential models. So the first thing we want to focus on is how do we tell the difference in the two models? Well, linear is going to look like a line. So both of these right here, A and C, these are both linear models. Because notice the data or the points on the graph are straight lines. What that means is that they have the same rise and run consistently. So if I go, this looks like up to and over 4. If I do that again, notice it's consistent. Always up to over 4, up to over 4, okay? Or we could go up 1 over 2, which is the reduced form of that. It's just because 2 over 4 is a half, 1 over 2 is a half. So just notice it's consistent ratio over time, okay? An exponential function or model has a different shape. Okay, so notice that in this case, it's kind of really slow and stagnant, but then as it grows, it grows quickly, faster and faster towards the end. This one's doing the same thing, but it's decreasing quickly and then staggering off, kind of almost like it's not really flatlining, but it looks like it is. So this is more like what we see in investments or when we're talking about decay of like a radioactive substance or something like that. These types, like compound interest is a really like a big one for people, the exponential growth. So when we talk about linear versus exponential, this is visually the difference between the two. Some things to note. This one has a positive linear trend because notice it's going upwards from left to right. This one has what we call a negative linear trend because it's going down from left to right, like it's falling downhill. This one is going to be called an exponential growth because notice as we go from left to right, we're kind of slow, but then we grow, grow, grow. And this one was high, 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 and then it falls off. So this one from left to right is called decay. So this is just visually what you need to know to recognize the difference between the two. Let's look at some other things we can use to tell the difference, okay? So a linear model will increase or decrease at a constant rate. Notice I talked about that same rise over run over and over and over again. What's happening for that to be true is absolute change. Remember, new minus old. We talked about that in class in week 2. It's the same over and over again. So you're repeatedly adding or subtracting the same amount when you go from one value to the next successive value. So like that's like getting paid $10 per hour. Every extra hour I work adds $10 to my account, okay? It's the same exact adding over and over and over again. And just to recall from our day 1 video, we learned that you can write linear models as y equals mx plus b. So the new model for us today is the exponential model. It occurs when the exponential function increases or decreases not at an absolute change, but at a proportional percentage rate. In other words, relative change or percent change will stay constant over each successive term. What that equates to is multiplying by the same thing or dividing by the same thing over and over again. So here's an example. If something is doubling, you're to go from one value to the next, you're timesing by 2 every single time. So if I get, frogs and I say, oh, the population of frogs doubles every month. Well, every month I would take the population I currently had and times it by 2. So I'd be timesing by 2 from moving from one month to the next over and over again. So that's an exponential model, okay? So these are the formulas. There's 2 different variations, and that has to do with whether or not we are growing or decaying, which means increasing or decreasing. So you have your future value that you're going to be solving for, your new amount. You have your initial value. So this is just one variable. We just call it IA. That's one number you're going to put in there. And then you have your relative change, which is your percent increase or decrease as a decimal. So if you're doing a percent increase, you'll be using the 1 plus, because you're saying 100% of what I had plus that percent increase. So it's like what we were doing when we did the markups there. And then 1 minus if we're doing a decrease. Okay, so think about 100% minus a certain decimal percent as a decimal. And then notice that would be decreasing our population or our value. Okay. So we talk about those terms 1 plus R and 1 minus R as percent increases or percent decreases. They also, if they're given to you in a word problem, if you see the words growth factor and decay factor, they've already done the 1 plus R and the 1 minus R. You already have that parentheses completely worked out. Okay. So a factor is what you multiply each value by to get the next successive value in the exponential function. And we will go over the growth and decay factors and the relationship to relative and percent change in the class. So all I wanted to do was do an example where we kind of talk about how do you tell kind of which one you have? And how do I write the model? That's the big thing. So writing and using an exponential model when given a percent increase or decrease. So let's look at this first one. It says the average price of a home in a town was $171,000 in 2007, but home prices are rising. So that's a key word there because that means we're increasing by 3% per year. Notice this is a percent change, not an absolute change. It's not increasing by $3,000 every year. It's increasing by the percentage of the previous year's base. Okay. So when you have a percent change, you're going to have an exponential model. And the reason for that is the increase is a percent change or relative change, if you want to think of it as a decimal, not an absolute change. So if you're doing linear, it's absolute change. It would be increases by $3,000 per year. It would be dollars, which is what our unit was in, okay? But if it's exponential, it's going to be rising or falling by a percentage or a relative change, okay? So do we use this formula, or this formula? Well, we're not using linear because it's an exponential model. So we're going to be either using this one or this one. That is why I underlined the word rising. Because we have a rising or increase, we're going to use this formula, okay? Because that's the one that has the 1 plus R. Write the model, okay? So A equals, our starting value for our house was 171,000, I believe. Yep. And we're going to write 1 plus. The R is going to have to be 3% as a decimal. So that's going to be 0.03. And then notice in the exponential model, I didn't say this earlier, the variable that's going to be in your formula, instead of usually an x on that side where we had y equals mx plus b, it's going to be t for time usually. So t is going to be our variable on this side of the equation. And we usually want to write that a little bit nicer by adding those two parts together. So that's 1.03 to the t. So there's my formula in its final form. Use the model to predict what the home will be worth in 10 years. Okay, so in 10 years, we're just going to plug that in for our time is 1.03 to the 10th. So I'm going to have, now this is where you'll have to use your calculator carefully. I usually do the 1.03 raised to the 10th and hit enter. I do not clear that. I leave that in there just so I don't round anything. Then times that by the number out front. So we're going to round this probably to the nearest whole dollar since the original price was rounded to the nearest whole. So this will be 22980, and then this 7 is going to bump that 9 up, so it'll actually be 810. So approximately $229,810. So 10 years, that house has been appreciating at a rate of 3% per year, which again is repeatedly multiplying by that 0.03 from the previous year, adding it to the base of what we had that year, and then continually doing that over and over again. So the reason that that's not linear, just to show you right here, is if you do the first year, I just want to show you real quick why this works. 0.03, then we add that to 171,000. So notice the first year we had a $5,130 increase. But the next year, we start with this as our starting balance, so times 0.03. Notice that's a bigger value. It's not adding the same dollar amount every year. It's adding a percentage, a consistent percentage each year. But that value, that money value, will be different because every year, the previous year's balance was more than our initial balance. Okay, so that's why it's slightly different than a linear equation. And then our last one for the pre-video day 2 stuff is this one. So there were 50 frogs put into a new pond. For each scenario, state if this is linear or exponential and write the model. Then use the model to find the population of frogs after 12 weeks. Okay, so we're going to be measuring by weeks. So that's our time instead of years. So each week, the population of frogs increased by 9 frogs. So this is an absolute change. We're increasing by a fixed number of frogs. Every single week, it's exactly 9 frogs. So we would write this as being linear. And our starting number of frogs was 50. Our increase per week is 9 frogs a week. So this would be y equals 9x plus 50. Remember, increase per week times x plus initial amount of frogs. So there's that one. The second scenario says each week the population of frogs increased by 12%. Notice this is a percent change, not an absolute change. Or you could say relative change if you think about it in its decimal form. So we're going to be using an exponential model here. And the initial amount is still 50 frogs. Our rate is going to be 0.12. And so when we plug that into our formula, initial amount of frogs, we're increasing again. That's also important here, increase. We're going to have 1 plus 0.12 to the t, and then we'll just simplify the inside of that parentheses. Okay, so that's the formula for that. Now I'm going to go back and do the second part of this. So I have both my formulas. So this time, if I want to see how many frogs would we have 12 weeks later, so we have 9 times 12 plus 50. So 9 times 12 plus the 50, that would be 158 frogs. So notice, if the frogs are growing linearly, which means an exact increase of 9 frogs every single week, we're going to have 158 frogs. Let's look at how many frogs we would have if they were increasing their population by 12%. So 50 times 1.12 to the 12th, because this is our weeks now, the t is our weeks. So 1.12 to the 12th, and then times that by the 50. Notice if we round to the nearest whole frog, that's going to be 195 frogs. So you see that exponential grows quicker, okay? It's because we're increasing by a percentage, which will get larger and larger values of frogs as we go from week to week, okay? Because you have more frogs, and then you increase your population by another 12% on the number of frogs you currently have. Whereas this is not ever going to see a difference. It's always going to be 9 frogs, 9 frogs, 9 frogs, 9 frogs. We're just adding 9 frogs every single week. Where this says we have to figure out 12% of what our current population is and add that each week. Okay, I hope this is helpful, and I will see you all in class.